very important for the future.
You write all those things in your introduction or your thesis?
Yes, I think. Because I explained in the literature review, I explained the explosion is accident. So
it should be in the introduction why you studied it. You know, give some significance. I think you should write something about that in the introduction. Literature review is about the nanoparticle explosion. Okay. So that is the significance of your study, basically. You have to get data to flood the information data. Okay. But you said just now, one of the reasons for explosion was pre-ignition of the material, right?
Yes.
But you said, in passing, I remember you said, for nanoparticle, pre-ignition is not the issue. Is it correct?
No, it's not.
It doesn't have pre-ignition.
For my material, it's not an issue. But for a more reactive material like titanium dioxide, chromium, it is a big issue because from your experiment you might underestimate the value of the explosion pressure. So they didn't cover that part yet, pre-ignition, because it's the limitation of the data. They only from the paper that I read, they only said that they disperse the material and they ignite it automatically. So they take the value without using any ignition source. So they say that it is more sensitive, so it is more dangerous for the more reactive metallic oxide, not metallic oxide, pyrophorous material that is in metal nanopowder. So for my carbon nanofiber and multi-wall carbon nanotube, I didn't experience this issue. But for other material in the literature review, yes, they have these issues, and they didn't cover this pre-ignition phenomenon yet. They didn't have explanation on why.
So in your report, you cite this thing, you cite the literature where you get from. Why do you need to, on the thermodynamics calculation, why the energy? Why do you need to look into a, what do you call this, beyond stoichiometric condition? You have to add that alpha inside that.
So if you, because we have difficult impact, especially in industry. The concentration is very large. So that's why the equation goes beyond the stoichiometric, whereby you have a large quantity of carbon. It is in excess. So it is higher than the minimum explosible concentration. So that's why I consider when we go above stoichiometric, when the amount of carbon is in excess. So not only that it undergoes the complete combustion, but the carbon also exists.
But that one is actually for carbon, isn't it?
Yes, carbon.
Not for nanocarbon, eh?
Yeah, this one is for carbon, yes.
Is there any information or data on the heat of nanocarbon?
As far as I have read, not yet.
Do you think they should be different from carbon? Carbonation?
If we consider the explosion severity, the Pmax, the finding is that it is comparable to the micron. So we can say that it is not much different from the micron for the carbon. Because from my explosion severity experiment, the data is not much different from coal. So you can say that it is comparable. We can use the thermodynamic for the carbon.
But that one is for multi-wall, multi-wall.
No, the thermodynamic is for carbon only.
For carbon only.
Yeah, general.
And
nanotube. Multi-wall carbon nanotube has a bit higher, but it's still comparable. The difference is less than 30%. The Pmax and also the KST. So it's not much different. And even when I compare it to coals, it is also within the range of the coals. So it can be said that for carbon nanomaterial, it is comparable to the one from the data from the carbon coals.
So then your study become irrelevant.
Because I want to prove. Because before this, the data is not much, it's very limited. For this carbon nanomaterial, I only found one paper which was published this January 2015. So my paper and his paper come to the same conclusion, whereby the explosion stability is not much different from micron. So my project here, we confirm the notion that it does not follow the cubic relation.
The cubic relation is for what then?
Cubic relation. This one.
You know, for what then? If it's not relevant to nano carbon, then this is for what? But why did people say it relates to this?
Because before this, this cubic relation is for you to determine the explosion index. So you have the DBDT from the graph, the volume is from your equipment, and they predict from the DBDT and for the volume, so you can predict the KST for different type of material with different type of the diameter. So previously they didn't have data on nanoparticle. They only said that for nanoparticle you can extrapolate this relation, and they said that it will be much more severe than the micron. However, we found out that it is comparable.
Did you set up a graph of this for as predicted for nano using this, and put it together with your experimental graph to show how far it went from?
I can do that, but I didn't have the data from the equipment. Equipment only, when I use equipment, they will automatically regenerate the graph. They didn't have the, I cannot find the Excel data for me to construct the graph manually, unfortunately.
Well, because people say extrapolation, why don't you just extrapolate? Just take one data from one literature, extrapolate something. And when you show it together, then okay, it doesn't fit this theory.
Meaning that you have to conduct experiment manually because we cannot generate.
But then
The
how
data.
can you determine the rate of pressurized if you do it manually?
I mean, you every time you conduct the experiment will be different set in order to get to the trend, the graph, because currently the equipment have very limited facilities, and then don't have automatic generated data, right? That's a problem with our explosion chamber right now. Maybe we can upgrade.
Is there any, never mind, okay, but I think that's another area that you can show to improve your paper, but maybe you don't have to do it, too late already.
Yeah, not now.
Anyway, what is the relationship between explosion severity and a dispersion model? What is the relationship? Is there any relationship?
Actually, I haven't seen the model yet. The model is also not yet explored yet. It's done by Koyu, but the relationship between dispersion and also the dispersibility. Because what I use here is the carbon nanopowder, and how I disperse it is I'm using compressed gas. So I have this chamber. I chamber. From the chamber, it will form a cloud. So from the cloud, I will have the ignition source. The ignition source will ignite the material. So the relationship is, you can say that for the explosion to occur, you must have dispersion first. So if it's not dispersed, then the possibility is very low for it to explode. So I think it's like that relation.
No, Ariffin, what's the difference if gas dispersed? They have some certain concentration
Yes.
mixed with air,
Yes.
and then it can explode because of it within the range of explosivity.
Yes.
What's the difference with dust, with nanoparticles? Will it be the concentration?
Oh, actually, I didn't put the pentagram, the 5 factor that can cause the dust explosion. So basically, the 5 factor is first the oxygen, and also the dispersion. You must have dispersion, and also you have the material, ignition, and the last part I didn't remember, but it is different from the fire triangle, whereby for this dust dispersion you must have dispersion for it to occur. Yeah, this one. So you have oxygen. Oxygen here is the oxygen. You have the ignition source. Fuel is the material, and the mixing between the material and the mixing between the oxygen and the fuel. Confinement. The mixing here is the dispersion. So for the dust explosion to occur, all these 5 things must occur at the same time. So it is different from the original fire triangle.
Okay, thank you.